Introducing the LT3080 adjustable 1.1 amp single resistor LDO regulator from Linear Technology. Welcome to the training module on Linear Technology's LT3080. This training module introduces the new architecture of the adjustable linear regulator from LT. The LT3080 is the first of a family of NPN LDOs that may easily be paralleled for heat spreading and are adjustable down to 0 volts with a single resistor. This new architecture regulator uses a current-based reference rather than a conventional voltage reference to allow sharing between multiple regulators by directly paralleling the pins. Current sharing is set with a small length of PC trace as ballast, enabling multi-amp linear regulation in all surface mount systems without heat sinks. With the introduction of the LT3080, the architecture of linear regulators has changed. This regulator throws away the voltage reference and uses a reference current to set the output. As shown in the figure, a single resistor sets the output for a voltage follower in the regulator. A precision zero temperature coefficient with 10 microamps internal current source is connected to the non-inverting input of the power operational amplifier. The power operational amplifier provides a low impedance buffered output to the voltage on the non-inverting input. A single resistor from the non-inverting input to ground sets the output voltage. The output voltage can be adjusted down to 0 or up to within about a volt of the input supply. Since the voltage at the set pin and the output are equal, these regulators can be easily paralleled to share current using only a small piece of circuit board as a ballast resistor. That allows heat to be spread across the board, eliminating heat sinks. Additionally, the collector of the output transistor comes out separately, allowing a drop-in resistor to be inserted in series with the collector. The LT3080 achieves high performance without any compromises. Featuring a 1.1 amps of output current and a wide input volt range from 1.2 to 36 volt, it has a low dropout voltage of only 350 millivolts at full load. The output voltage is adjustable, spanning a wide range from 0 to 36 volts, and the on-chip shunt current reference achieves an accuracy of ±1%. The wide V-in and V-out capability, low external parts count, and parallel capability makes it ideal for modern multi-rail systems. Output voltage noise is as low as 33 microvolts RMS over a wide bandwidth of 10 Hz to 100 kHz. Protection features include current limiting with foldback and thermal limiting. Packaging is compact and thermally efficient. The LT3080 generates a 10 microamp reference current that flows out of the set pin. Connecting a resistor from set to ground generates a voltage that becomes the reference point for the error amplifier as shown in the figure. The reference voltage is a straight multiplication of the set pin current and the value of the resistor. Any voltage can be generated, and there is no minimum output voltage for the regulator. A minimum load current of 1 milliamp is required to maintain regulation regardless of output voltage. For true zero voltage output operation, this 1 milliamp load current must be returned to a negative supply voltage. A parallel regulator pair is shown in the figure. Although only 2 regulators are shown, any number of regulators can be paralleled for a higher output current. All the regulators have their inputs, their set pin, and their outputs are tied together. Inserted in series with the output is a small piece of PC trace to act as the ballast resistor. An output capacitor is needed for stabilization of the regulator since several devices are now paralleled. The output voltage is adjusted in the same way with a resistor to ground, but instead of 10 milliamps, there are now n times 10 milliamps, where n is the number of regulators in parallel. The LT3080 may also be paralleled with fixed output regulators to supplement the output current of a single device. This is useful when the single device does not provide sufficient current or a simple system modification is needed to increase the power supply current because of system changes. It is necessary to use 15 to 20 milliohms of ballast resistance to cause the two ICs to share. But since the fixed regulator like the LT1963 3.3 volt does not have a set pin, the point for connecting the set pin of the LT3080 must be for a divider from the output of the fixed regulator provides a voltage about 4 mV lower than the fixed output to ensure that the output current of the LT3080 is zero under a no load condition. The thermal advantages of directly paralleling regulators are shown here, resulting in reduced hotspots. In the example shown on the last page, two LT3080 DFN devices are mounted on a 1-ounce copper 4-layer PCB board. They are placed approximately 1.5 inches apart, and the board is mounted vertically for convection cooling. Two tests were set up to measure the cooling performance and current sharing of these devices. The first test was done with approximately 0.7 volt input to output and 1 amp per device. This gave a 700 milliwatt dissipation in each device and a 2 amp output current. The temperature rise above ambient is approximately 28 degrees, and both devices were within plus or minus 1 degree C. Both the thermal and electrical sharing of these devices is excellent. The thermograph in the figure shows the temperature distribution between these two devices, and the PC board reaches ambient temperature within about a half an inch from the device. The LT3080 offers numerous advantages when it comes to dealing with noise. There are several sources of noise in a traditional linear regulator. The most critical noise source for any LDO is the reference. From there, the noise contribution from the error amplifier must be considered, and the gain created by using a resistor divider cannot be forgotten. The LT3080 does not use a traditional voltage reference like other linear regulators, but instead uses a reference current. To lower reference noise, the voltage setting resistor may be bypassed with a capacitor, though this causes startup time to increase as a factor of the RC time constant. The LT3080 uses a unity gain follower from the set pin to drive the output, and there is no requirement to use the resistor to set the output voltage. The unity gain follower presents no gain whatsoever from the set pin to the output, so noise figures do not increase accordingly. In some applications, it may be necessary to reduce the power dissipation in the LT3080 package without sacrificing output current capability. Two techniques are available. The first technique employs the resistor in series with the regulator's input as shown in Figure 1. The voltage drop across RS decreases the LT3080's in to out differential voltage and correspondingly decreases the LT3080's power dissipation. The second technique for reducing power dissipation, shown in Figure 2, uses a resistor in parallel with the LT3080. This resistor provides a parallel path for current flow, reducing current flow through LT3080. This technique works well if input voltage is reasonably constant and output voltage current changes are small. Current sources are useful components in many types of applications. The LT3080 can provide a two-terminal current source with very good DC performance. The requirement that the LT3080 include an output capacitor to provide frequency compensation makes the device slightly less useful since it cannot be used as an AC current source. However, the very high gain of the LT3080 allows small voltage drops to set up the output current and produce very high DC output impedance. Frequency compensation is achieved with a capacitor from the input pin to the output. By configuring the frequency compensation as shown, the current through the capacitor is included within the feedback loop and does not appear as capacitance across the device. If the input voltage changes, current flows through the capacitor due to voltage change. When the current in the capacitor approaches the DC current, the loop will not be able to compensate for the AC current, and the AC output impedance will decrease. The LT3080 can easily be configured as LED drivers as shown in the figure. The ability of the LT3080 to operate down to 0 volts makes it attractive to use this for general purpose lab supplies. The power dissipation for a lab regulator can become very high if the operating voltage range is high. The circuit in the figure shows two LT3080s connected to keep the power dissipation down by controlling the input voltage.